Okay, so here's setup for this one, for number 48. And they say these points are on a line. So if these points are on a line, what about the relationship between x and y? Yes, of course it's linear, but better than that. X and y are proportional, is that true?
Yeah.
Are x and y proportional? No, not a chance, right? Not a chance. If x and y are proportional, then when x was 0, y would have to be 0. And they'd have to grow at a relative rate together. Proportional relationships look like this. This is what proportional relationships look like. Lines that go through the origin. When one is 0, the other is 0. Like our scaling up the picture, remember the photo? So not only in that, for the photo, you had the height and width were proportional. But if we're talking about the line that goes through, we're talking about the line that goes through these 2 points, y and x are not proportional. But what? Changes in x and changes are proportional to changes in y. And what do we call that? Constant rate of change. Someone said constant rate of change. Never forget it. That's the best line through those points that I've drawn all day. Okay. So, if you have a linear graph, that's saying that the change in x is proportional to the change in y, and that we have constant rate of change between y and x, constant rate of change. So it says, what's the slope of the line? Slope is? You know your formula, but now we know what that's representing. What is y2 minus y1? What does it represent? Change in y. We started at y1, we end up at y2. The difference is how much y changed. Same with change in x. Okay, so what do you get when you do this? Quick. Negative 0.93 minus 4.74 divided by 8.1 minus, what is it? 0.8. Negative 0.9. Negative 0.9. Okay? And that's a ratio, or a quotient, negative 0.9. So can we interpret that number relative to y and x? So what does that tell us about y and x? Negative 0.9. This is the whole ball of wax right here. This is what it's all about. As x changes how much? If x changed by 1, then what would y do? It would go down negative 0.9. What if x changed any amount? What would y do?
By negative 0.9.
Whatever x changes by, y is going to change by negative 0.9 of that, times that. That's right, of that, times that. Changes are proportional. Another way to say it is that y is changing negative 0.9 times as fast as x is changing. Remember, relative change. A quotient means relative change. So that negative 0.9 is telling us how much faster y is changing than x. Y is changing negative 0.9 times as fast as x. That's relative change. Okay? What's next? Necessary to go. Oh, so they're just saying what's the change in x? Am I right? Are they just asking about this?
Well, you go from
1.8 to 8.1?
From
Oh, to x equals 5. Sorry. All right, so to 5 will look like this. So they're saying go from 1.8 to 5. And they say represented on the graph? It's represented as a horizontal line from 1.8 to 5. What is that change in x? 3.2. And now we have full command of the subject. We know exactly what y is going to do. What's y going to do when x changes by 3.2? If y is changing negative 0.9 times as fast as that, how much is y going to change?
Negative 0.9 times negative 2.
It's going to change negative 0.9 because y is changing negative 0.9 times as fast as x. So therefore, it's going to be negative 9 times 0.32. And what changes that?
Negative 2.88.
Negative 2.88. I'm kind of guessing what the questions are here. And they're going to ask you, what's the new value of y, right? Okay, so is the new value of y negative 2.88?
Yes.
Nope, that's how much we changed, right? That's how much we changed from here to here.
It's 4.74 minus.
So if we started at 4.74, we went down this much.
1.86.
So 1.86 is the new value of y. If x changes by 3.2, the new value of y is 1.86. What else did they ask? Repeat it, so we don't need to repeat it. Vertical intercept. How will we find the vertical intercept? Same thing. So we can find the corresponding change in x that would get us to x equals what?
0.
0. So that change is?
Negative 1.8.
Right, negative 1.8. Thank you. Getting better with this thing. Negative 1.8. If x changes by negative 1.8, how much does y change?
Negative 1.8 times 0.9.
Negative 0.9 times as much as that. See how easy it is when you understand it? Thank you. This is not your grandmother's pre-calculus. All right, negative 1.8 times negative 0.9. Got to turn our brains on. But if we do, the result is good. How much did it change?
1.6.
1.62. So is that the y-intercept?
No.
Nope. Got to add it to 4.74. Add 4.74. We're going to go, if we go back 1.8, we're going to go up 0.9 times 1.8, right? And that's our 1.62. So we add that to 4.74, gives us the vertical intercept. 6.36. Any questions on this problem? Yeah.
Tests and all, like when we're writing things down, like,
Yeah.
do you want things very like, I guess descriptive? Like, I always like y-intercept equals at the end of every problem and square it. Does it matter like for the test or anything like that? Like, if I were to
So-
write this out kind of like you did.
Sure.
you really-
Yeah. So I was talking as I was writing. So this is not a good formal write-up of the solution.
But we
Okay.
didn't got any homework or anything back.
Okay. So
Most teachers make you.
show all your work. First of all, show all your mathematical work. Whenever it says explain or write something, use complete sentences, and don't cut it short. Don't try to cut corners.
So if it just says
like square our answer, right? Like in all my past math.
Yeah. So it's about understanding here. So I don't have very strict format for your homework. Don't worry about that. Yeah. I want you to make sure you understand the material.
Like if you just use points of the formula, so you take points out.
So we're all about understanding what's going on. And when you get to the test, if you just have a bunch of formulas memorized, it's not going to go well. So I encourage you to try to start learning in terms of concepts and ideas rather than formulas.
So if you don't both, like it's like
I'm telling you, in the long run, the formulas don't get you where you need to go in calculus. Calculus is about ideas, understanding how things change together, and that's what we're doing with. So if you just really are just always dependent on formulas, it's not going to end up well in the end.
because it asks you to represent it on the graph, a lot of them. And so if we just, as long
Ver-
as our graph shows all,
Horizontal lines.
then
Horizontal and vertical lines represent changes in x and changes in y. Other questions? Okay. Next one we said was 74. Okay, 74 is a good one. So in 74, I got it all ready. I was hoping you'd ask for that one. Okay, how did I do on defining these variables? T equals time, D equals distance. Do pretty well? Okay, time in what? Time in seconds. In minutes or seconds? It's seconds. Okay, and distance in feet? I think it's feet, right?
74.
Oh, I'm doing 78. Sorry. We're doing 78. Feet. How about this? This is the restaurant problem. Sorry. Driving away from the restaurant. Did I define these well? Time in seconds, distance in feet. No, not at all. What time? What distance? We could name 5 different distances relative to the situation. So we want to make sure we know. So what time is it? Time since what? Leaving the restaurant? I don't think so. Yeah, time since he began driving. Because we're going to see in a second, he doesn't start at the restaurant. So this is time since he began driving in seconds. All right, what about distance in feet? How about distance traveled in feet? Is that better?
Does it matter that they said that he's going north?
It says his car's distance north of the restaurant. Is that the same as distance traveled by the car? That's different. It's not the same thing. Distance traveled won't do it. Okay, we'll see it again in a second. So we want the distance north of the restaurant in feet. That's important. Okay, distance traveled is different. It's different. Okay, so here I've got it all by time increments of 1/2. So what is the distance north of the restaurant? How do we find that?
Well, you have the formula D equals.
It equals to 2 times whatever t is squared minus 7. What does it mean that it starts as negative? South of the restaurant, right? So this is south of the restaurant. So would distance traveled make sense for this problem? For D? Distance traveled? No, at 0 seconds, what distance has he traveled? How many? At time 0, what's the distance traveled by the car? 0. We're starting, you can't travel, no time has gone by. So this distance is like a position, you see? It's not a distance traveled. That's why, there's an example of why it's so important to define your variables well. Because if you just write distance traveled, that's not what this is. This is a distance from a reference point. Okay? Spreadsheets are amazing things. They're so helpful, right? And you've got these laptops sitting right in front of you. Okay? So yeah, so you just put the formula in. I put the formula in terms of my A cell. And then I can just grab it, and it just repeats it for all of them. So this gives us a picture of what's going on. Okay? So at t equals 1, we talked about that. Negative values here up till 2 seconds mean he's south of the restaurant. Okay, find the average speed of the car from 3 to 5. So we said average speed is? Average speed? Okay, that's how you calculate it. Average speed then will be the change in distance, or change in our d variable over change in time. Okay, so what's the change in distance from 3 to 5? So we need the distance from the restaurant at 3 seconds, which is 11. Distance from the restaurant at 5 seconds, which is 43. So what's the change in distance? 32. 43 minus 11. And what's the change in time over that? 5 minus 3. You can't cut corners here. This takes, you have to plug both 3 and 5 into D. Get those distances from the restaurant and then find that change in distance. Okay, so we get the number. So over here I can just do that, equals 43 minus 11, divided by 2, 16. Feet per second. Okay, here's what we want to really talk about here. Between 3 and 5 seconds, did the car go 16 feet per second? Constant rate from starting at time equals 3 to time equals 5. Did it go 16 feet per second? Constant rate. No, what's happening to the car as it leaves the restaurant? It's going faster, so every time increment, the distance is going to increase. And you can see that right there on the table. Down here, in the first second, 6 feet traveled. In the last second that I've showed, 18 feet traveled. Not constant rate of change. But for this speed, we got one single number. He's speeding up over that 2-second time interval, but the speed is one single speed number. So how can that be? So what does this number 16 mean? What is that, the average? Yeah, what is the average?
Which means that through that time period, he was traveling approximately 16 feet per second during the time.
Doesn't need to be approximately 16. He could go like super slow for 1.9 seconds, right? And then go super fast for the last 0.1, and his average speed could be 16 feet per second, so he never went close to 16 feet per second, do you see? So what does this number mean, 16 feet per second? Is 16 feet per second, is that a changing speed or a constant speed? 16 feet per second? It's a changing speed? What did it change from what to what? It's always 16. That's a constant rate. Average speed is a constant speed, or is the constant speed. Which constant speed is it? Is it the constant speed that this car traveled in those 2 seconds? No, it didn't travel at a constant speed. It sped up through those 2 seconds. But 16 feet per second is a constant speed. What constant speed is it? What's that? No, this is speed. It's not acceleration. It's kind of like there was someone. Go ahead.
It's the distance traveled in a certain amount of time.
Okay, right. It's kind of like someone else at the restaurant or near the restaurant on a bike. And at time equals 3, where is the bike and the car? At the same place, okay? So at time equals 3, both the bike and the car are 11 feet north of the restaurant. The car does what? Speeds up over those 2 seconds. The bike goes 16 feet per second at a constant rate for those 2 seconds. Where are they both at 5 seconds? Same. Now they're both at 43. So average speed, the average speed of the car is like the trip of the bike going at a constant speed at 16 feet per second for those 2 seconds. Does it make sense? So it's kind of like it's kind of like a phantom vehicle or something else that traveled the same distance and the same time, but went at a constant speed. That's what that number 16 means. So it's the average speed is the constant speed to travel the same distance in the same time. The car does not go 16 feet per second. It's constantly increasing in its speed. But that number represents something else that achieved the same distance at the same time, but went at a constant rate. Really important concept. Does it make sense? Okay. If we have all these values of t and d, these questions are pretty easy. As the time went from 1.5 to 2 seconds, by how much did the distance change? So you got to find that distance at 1.5 seconds, find that distance at 1 second, and the change will be the difference. So that would be 3.5 feet, 1 minus negative 2.5. So from 1.5 to 2, the car went 3.5 feet. How much time did it take to travel from 20 to 30 feet? Well, sometime between 3.5 and 4 seconds, it hit 20 feet. How do you find that time? Yeah, so you're going to need the formula 20 equals 2t squared minus 7. And you're going to have to get that time corresponding to 20 feet. And then 30, again, 30 is some time, 30 away from the restaurant is some time between 4 and 4.5. You're going to have to plug 30 into the formula. 30 equals 2t squared minus 7. So, anybody know what this is? 3 point what? So 27 divided by 2 is 13. Square root of 13.5. What's that? 3.1. Square root of 13.5. 7. 3.7? Okay? And then we got to find the time when it's 30 feet north of the restaurant. So that's going to be 37 divided by 2. Square root. It's 37 divided by 2. Square root of 18.5. 4.3. So this takes some work. You got to find the time that it reached 20 and the time that it reached 30. And now we've got those two time, and we can do 4.3 minus 3.7 is the change in time for that change in distance. Is that 0.6? So if it went from 20 to 30, why can't we just do, can we just do 10 equals 2t squared minus 7? Will that work? What is that finding? What would that be finding if I did that?
The time it took him to go 10 feet.
Yeah, the time it took him to get to 10 feet north of the restaurant, which is totally different than the time it took to go from 20 feet to 30 feet. You see? So you can't do this. You can't do that. You got to find the time it took to get to 30, the time to get to 20, and then subtract the difference between those two will be the change in time. What happened to my beautiful spreadsheet? There it is. Questions on this problem? You cleared up? Are you good? Any questions on the? We're gonna go on. So, what is average speed? This is a key concept. Average speed is, first and foremost, it's a single number, so what is it? It's a constant speed. What constant speed is it? Travel the same distance in the same time as whatever you're finding the average speed as of. All right, so here's a little practice. So this is fun. Here we go. John and Jane taking a walk. Here they go. That Jane, she's a crazy walker. All right, let's see it again. All right. So think in terms of what is this demonstrating? Watching John and Jane walk here, what is it demonstrating? What is this illustrating? What idea? You say constant speed. Tell me, what's constant speed? John is traveling at a constant speed.
Same distance, but Jane has variable speed.
Jane has a changing variable speed. Okay?
But the average.
The average.
The average speed of Jane is the same as John's constant.
He said that the average speed of Jane is the same as John's constant speed. What do you think about that statement? Way in the back, she likes it. Like it? So, well, yeah. John is representing the average speed of Jane. That's what this is showing. John is representing the average speed of Jane because John It's the constant speed that goes the same distance as Jane in the same amount of time as Jane. Okay, and then we know that that is calculated by average speed, the change in distance, over the change in time. So in different scenarios, different types of problems, you could find these values in different ways, but it always comes back to how much did the distance change, how much did the time change. So you might be given a graph, and you're going to have to pick off changes in distance, changes in time, or you might be given a formula, and you have to calculate changes in distance and changes in time. Okay, so let's open up, but we're going to move on to Module 3. So in Module 2, we learned all about proportionality. We talked about 3 different ways of thinking about proportionality. And then we moved to if changes in a quantity are proportional, changes in 2 quantities are proportional, that's constant rate of change. And then we talked about average rate of change. So those are kind of the 3 big ideas of Module 2. Proportionality, constant rate of change, and average rate of change. So now in Module 3, we're really going to dive into the way that we represent quantities that change together, and that's with functions. Functions is the notation and the way that we think about 2 quantities changing together, whether that could be proportional, it could be constant rate of change, or it could be something else. So functions can model all kinds of ways that 2 quantities vary together. Okay? So we're going to look at this box problem. So let me kind of lay out the scenario for you. Where are we? It doesn't matter. Oh. There we go. Okay. So with the box scenario, the first thing is you've got a sheet of paper. Okay? And then you're going to choose some size of squares to cut out of the paper. So I got my paper, and I'm going to draw squares, and I'm a super fast square drawer. Okay? All right, so I got the squares. And the next thing that you're going to do, and so those squares are variable in size. I can make them real small ones, or I can make them larger, cut out more of the corners. But they're always a square, and all 4 are always the same. Okay, so now I'm going to cut those out. And a super fast cutter. And so I cut out the squares, right? Okay. Now what I end up having is flaps. And so if I draw dotted lines from the corners of the squares, those are flaps that I can fold up and I can make a box. So I fold up the sides like this, and you get the box. So that takes a lot longer than you think. Try that at home. It takes like 5 minutes to do this. Anyway, okay, so you get this box. Do you see how it worked? Draw the squares, which are variable in size. Once you pick a square, though, you do all of them that size. Cut them out, fold up the flaps, and you get a box that has an open top. Okay? So what I want you to do is work on page 85. Okay? So let's go through. Let's see if we can do numbers 1 and 2 on page 85 and 86. So it's 1.5 pages. Go slow. Don't move on to something until you understand what you did before. Work together. Talk it out. Here's the box. Okay, so our cutout length is going to be 1.5. And in number 2, I'm going to change the wording just to clarify. For A, you want the width of the box in terms of the length of the cutout. So add in the terms in terms of there, so it's clear which we're doing in terms of what. So 2A, width in terms of cutout length. 2B, length in terms of cutout length. And same with C. Area in terms of length. Cutout. Okay, I'll make one round for questions, and then we'll talk about it. How'd it go?
Just the box confuses me.
Yeah, okay, so we'll do that. Okay, so what happens to the box when you choose different cutout lengths? So if we choose a really small square, what kind of box do we get? Yeah, and also like flatter, bigger, flatter, but really shallow. And then if I make this cutout larger, what happens to the box? Deeper, but taller, but then the base gets smaller, right? So here we are at 1.5. So they asked you, with a 1.5-inch cutout, something like that, the way I said, so what will the length then of the box be? What will the length be of the box? Where'd you get 8? Yep. Good. Okay, so the original length of the paper was 11. We cut off 1.5 down here. We cut down 1.5 up here. So when we fold this up, that dimension will be 8. So length will be 8. What about the width? Same way. We end up subtracting 3, or 1.5 times 2, from 8.5. So 5.5. What does the height of the box turn out to be? What's the height of the box? Same as the cutout, right? It's the width of that flap. So when you fold that flap up, you're going to get the same. You're going to get the same height of the box as the cutout. So now if we let the cutout be any value, call it x. X inches by x inches. So they wanted a formula for what's the resulting length of the box in terms of that cutout length x. So what did we do? We started with a piece that was 11. And how do we get the length then from that? Minus 2 x's, right? We minus an x up down here, and we minus an x up there. And so our length is always 11 minus 2 times whatever the cutout length is. Okay? W in terms of x. The original width was 8.5, but we're taking away how much from the width? An x on this side and an x on this side, minus 2x. And what's the height equal to in terms of the cutout? It's always x. Okay? So the question is, if we get to that table in E, the table in E says, what's the smallest possible value of x? Okay, so we want to think of what's the smallest possible value of x, meaning that it's physically possible. Physically possible, how small of x could we make it? That's a physically possible situation. 0.5. Can we make it smaller than 0.5? Right. And so, but what is possible? What's the smallest cut I can make? Just that's possible. No, I can go smaller than that. 0.01. I can go smaller. But it is physically possible for me to take this piece of paper. Where's my piece of paper? And cut a side length of 0. I know that it doesn't make a box, and that's really uncomfortable. But it's physically possible for me to cut a cutout length of 0 long. Watch me do it. I just did it. And so what happens? I get this. I know it's very uncomfortable that it's not a box. But it's okay to make x equal to 0. Isn't it okay? You just get this flat sheet of paper. Can I make x negative 1? That's impossible. But 0 is possible. You want me to do it again? Just did it. Okay, so 0 is possible. I know it doesn't make a box, but it's possible. So what's the largest value of x that I could cut? What's the largest value of x that I can cut? 8? 5.5?
4.
What's
4.25.
that's the largest cut I can make right there. What is that value of x?
4.2.
Half of the width, 4.25. It's the biggest I could cut out. Do you get a box? No, you just get this piece of green paper right here. But it's physically possible to do it. Can I cut bigger than 4.25? No. Okay? What I want you to do for Friday, I want you to finish worksheet 1 for Friday. Finish worksheet 1. Go slow, think about it. Don't rip it out. Leave it in there. Finish worksheet 1 for Friday. Okay.
I totally forgot to pull it out.